So far, we've given you a bit of homework on the pre-processing part. In this lecture, we will give you some more. You have plenty of room for fine-tuning, as in our previous videos we simply reuse the MNIST structure. However, we don't have the data to reach an outstanding accuracy, like in the MNIST. We will give you some guidelines, but don't get discouraged if you can't get above 85% accuracy. Sometimes you have the best tools, but insufficient data. You will achieve the biggest improvement when adjusting the width and depth of the algorithm. I would like to leave a note here. Many problems may be solved by simply increasing the width and depth of the algorithm. There are some extremely deep nets with hundreds or even thousands of hidden layers. Our data is not as complex, but it may be worth it to practice your TensorFlow skills by creating 5 or even 10 hidden layers. Similarly, the number of hidden units can be increased to 1,000 or 10,000. However, both the width and the depth are very computationally expensive. I don't recommend you increase the hidden layer size to 10,000 on your home computer. If you increase the depth too much, even let's say 100 hidden units, may cause your computer to freeze. The next thing we can focus on are activation functions. Think about their graphs and how they would change the data. For example, a ReLU activation at the first layer would cause many hidden units to be zeroed because of the way it behaves. This may prove problematic, as you may make many nodes useless. However, in the MNIST problem, that was exactly what we needed, to clear up the inputs. What about the softmax? Quite often, the softmax is the activation function for the output layer, but we don't want to include it in the hidden layers before that. That's because it would scale all inputs in the previous layer to probabilities. Moreover, it would do so relative to the other inputs rather than independently. It is possible to lose a great amount of information about the variability of the data. Thus, you must be careful with it. Next, you can fiddle with the batch size. A batch size of 1 equals the stochastic gradient descent. It will cause the algorithm to learn quite quickly, but not so accurately. You should try applying batch sizes that will likely preserve underlying dependencies. In addition, you can also experiment with the learning rate, although that may not be as fruitful, as Atom adapts it dynamically. What you can do is visit the TensorFlow website and check out other optimizers comparing their performance to that of Atom for your specific problem. Alternatively, you should be able to go to the module tf.contrib. That's where the TensorFlow community contributes to the framework. You may find quite interesting methods that are not part of the core TensorFlow framework. There are really a ton of resources available out there. Finally, I encourage you to take your own data and try to implement this methodology in order to solve a given problem. If you don't know where to start, Kaggle is a great place to search through datasets. Moreover, a lot of people share their own code, so you can see how they approach the same problem you tried. Some people will use TensorFlow, others will be bet on sklearn. In any case, you will surely find people with a machine learning level similar to yours. Okay, let's wrap it up here. This was our real-life business case example. Thanks for watching.